And we know, because of last lesson, which I know feels like ages ago because we weren't here last week, we know that the temperature of boiling water just normally, on a normal day, was about 100 degrees C. So the temperature of boiling water on Mount Everest is quite a lot less than it is in this lab. Okay, because remember you were boiling water and you found that it was about 100 degrees C when you boil water. Okay, and today we're going to talk about why that is. So, yes, we're doing experiments. So let's go back up to the top. The effective air pressure on the boiling point of water. So high up a mountain, the atmospheric pressure is lower than at sea level. And this is because when you're high up a mountain, you've actually got less air pushing down on you. If you think about at the moment, when we're sort of around about sea level, we've got loads and loads of air above us. But as we go up, we've got less and less air above us. So we've got less and less atmosphere pushing down on us. Yes? Yeah, exactly. So if you got higher up, yeah, you've got less gravity acting on you as well. So yeah, you can technically, it's not that much, but technically, yes. Yeah, you can. No, it's not quite like outer space. So you wouldn't be like the moon where you're like walking like that, but you would feel slightly lighter. Yeah. So you got less atmosphere pushing down from above. You put it down somewhere, please. Thank you. Water then boils at a lower temperature as the water molecules, or the atoms that the water is made up of, can escape more easily because they've got less things pushing down on them. Okay, so that's why the temperature on Everest is less than the temperature of boiling water on Everest is less than it is in this lab, because there's less atmosphere pushing it down. There's less stuff holding it in place, so it can escape easier. Okay, right. So you may have a pressure cooker at home. Food cooks more quickly in a pressure cooker than in a normal pan open to the atmosphere. This is because the boiling temperature of water is higher at high pressure. So if you put something under really, really high pressure, then it boils at a higher temperature, so it cooks quicker. So up Mount Everest, there's less pressure, so it boils at a lower temperature. In a pressure cooker, there's more pressure, so there's more things holding it together, so it takes more energy, more temperature for those water molecules to escape. Okay. So why does air have pressure? That is the question. And that's what we're going to look at now. So air is a mixture of gases that form the Earth's atmosphere. Does anyone know what gases are in the air? Yeah? There is nitrogen, yeah. Yeah. Yeah, very good. Well done. So nitrogen, oxygen, and carbon dioxide. Very good. It's mostly nitrogen. Most people think, quite often they assume that it's just oxygen, because we know that we breathe oxygen. But the air is mostly nitrogen. Okay. So there's a lot of different gases in the air. And there are about 1,000 grams of matter in 1 meter cube of air. Okay. And the pressure caused by the air, or any gas, is due to its particles colliding with each other and with the walls of the container or other surfaces. So basically, gases are lots and lots of little particles. You might have talked about this in chemistry already, you might not have. They've got lots of particles and they like bounce around, okay, and they fill the amount of space that they're given. So if I let a gas go from here and I shut the doors and the windows, they would fill this room and they would move around and they'd bounce around. The more energy they have, the more quickly they move around and the more they'll collide with of the particles or the walls or the surfaces. Okay. More energy generated and more pressure as well. So the more they collide with walls, the more they hit walls, the more they hit each other, the more pressure they have. Okay. So there are some effects of air pressure, and I'm going to show you a few examples just now. Now you might have seen some of these already, especially if you've been to open morning in Hutchie, because we show this off. So what I'm going to ask you to do is get up and just come around this front desk over here, please. Yeah, I have what? Your ordinary marshmallows that I'm doing. Marshmallow, okay. I'm going to pop it in there. Then what I'm going to do is I'm going to put the lid on. It needs a nice good seal. So I'll put the lid on there. Okay. So at the moment, that marshmallow has got air pressure pushing in from it outside. It's also pushing out from the inside. So it's got equal amounts of air pressure pushing out and in. So it shows it's normal, normal shape. Okay. And all of you have got equal amounts of pressure pushing out from inside your body and pushing in from outside. And that's what stops you exploding. Okay. If you didn't have air pressure pushing in around you, then all that air pressure suddenly disappears. So if the air disappears, then all you have is pressure pushing out from inside your body. And you're able and it's flows. Okay. Yes, basically. So it's really important that we have this equilibrium. What we call equilibrium. We have the same amount of pressure pushing in on us and the same amount of pressure pushing out from inside of us. Okay. Same as that marshmallow. Okay. That marshmallow. This marshmallow has pressure pushing in and it's pushing pressure out as well. So it's equal. Okay. Balance. If I take away the air from inside of this, then the pressure pushing in and keeping it in shape is going to disappear because the air disappears. So what's going to happen to this marshmallow? What do you think? It's probably not going to explode. I'm not that good, but it is going to. Well, let's see. It's getting bigger. The pressure inside that marshmallow is pushing out, and it's got nothing stopping it anymore. Well, we'll see. So the only way I can get to that marshmallow now. Yes, because I've got most of the air out there now. Yeah, you can get machines that can strip the air out and it looks exposed, but so you can see it's pretty big. But I can't get that now. The only way I can get it is to actually let the air back in. And what do you think is going to happen when I let the air go back in? Yeah. I want to eat that marshmallow. Oh, there you go. Yeah. So, same thing would happen with you if you went somewhere where there's no air, so maybe outer space. Okay, you didn't have a special spacesuit on. You went out into outer space. The pressure inside of you would still be pushing out. You'd have nothing balancing it, so you would go explode. But see, you don't when you come back to Earth, you turn into a marshmallow. No, sadly not. No. There's other, so if you went down to the ocean, okay, you'd have your normal pressure pushing out, but the ocean would have so much more pressure, it would push in on you. So if you went down really to deep depths of the ocean, yeah, it would implode. So the pressure outside would be much bigger than the pressure inside. So pressure in, you would like basically crush like that. You'd like, oh my god, you would run out of air a lot quicker. Right, another example is this here. Okay? So just a normal piece of rubber.
What if we all try together? Yeah, guys, let's go. Lid up here, okay? And what I'm going to do is I'm going to connect it to another lid. Now, sometimes this doesn't work very well, okay? So, yeah, just put it together. Same as I. That's going to pop down. And then I'm removing the air from inside of it. So what's happening here is the pressure pushing them apart, the air is being removed, so we've just got pressure pushing from the outside in. So hopefully, I hope it does. Oh, that helps. I hope it does. Come on, Daniel. Come on. No, but if it doesn't work, we can all try it again. Listen, let us all try it. This is our number. So that's like it's so we keep it off. All right, Daniel. Daniel.
Okay. Listen. Still waiting. So if we're lucky, if we've got time, we can come back and have a play with that around with those again. I'll let you guys have a play with the marshmallows, okay? So we talked about that pressure. We talked about those particles like moving around and causing that air pressure. So what we're going to look at now is a little bit more into what causes, what are those particles? So kinetic theory of matter is the suggestion that all solids, liquids and gases are made up of tiny little particles called atoms and molecules. So a molecule is two atoms, more than one atom together, okay? They are far too small to see. They're about 0.000000001 meters. So teeny, teeny, tiny, very, very small. You can't see it unless you have a very powerful microscope. and they're constantly on the move. So what evidence do we have for this theory? So I'm going to show you a video clip in a second, and it's on Brownian motion. So this is the person that realised that particles, that everything was made up of tiny particles. So Brownian motion is named after a Scottish botanist, so a biologist, Robert Brown, who was the first scientist to observe the effect. So I will show you this video just now. Let me get it up. We saw that they put some particles of smoke under a microscope light, and then see them sort of like randomly moving about and jittering around. So we've got a path taken by a speck of smoke. We've got a little square there. So what we're going to do is basically random movement. So like this, like random, okay? Whatever you want to do. You can even close your eyes and do it randomly if you want to. So a random path.